So hopefully everybody spent their weekend studying statistics. All right? Last time we did section 4.3, which is the last section in chapter 4 that we're going to do. There are 2 more sections in that chapter, but we really don't need them in a class for statistics. You need them for a class in probability. So we're going to skip those sections. So any questions over section 4.3? No questions? That homework is due tonight by midnight, so don't forget that. All right? Probability, easy stuff. Well, the next chapter, next couple of chapters, are still about probability, but at a little bit different level, I guess is the word I want. So, section 5.1, which is what we'll start today, all of chapter 5 is about probability distributions. And section 5.1 is discrete probability distributions. Hopefully I got a better marker than that in here. There we go. So first of all, the word distribution. We've been using that word now since you were a little kid in statistics, right? Like distribution of height, distribution of pulses, all that. Well, it's the same idea. A distribution tells you what values are possible, and then its probability distribution tells you how likely those values are. Okay? So let's start with a really simple example. Roll a 6-sided die. We'll assume it's a fair die. If we let x equal number of spots that pop up, then x is a numeric variable, right? You can get 1, 2, 3, 4, 5, or 6. So this is a kind of a new concept. We've been doing this, but we didn't give it a name. This x is referred to as a random variable. Okay? So, what is a random variable? This is one of the hardest definitions that you're going to get all semester. So get ready to write this down. All right? A random variable is a variable that's random. Got it? Oh, you don't like that one? Okay, let's say it this way. It's a variable whose value depends on the outcome of a probability experiment. That's a hard way to say, oh, it's random. Right? So, random variable just means it's a variable, but we specify that it's a numeric variable. All right? For what we're going to do. It wouldn't necessarily have to be. We could talk about, the outcome of some ordinal thing, like you randomly select a student and what's the probability that they are a freshman? What's the probability they're a senior? That's a categorical variable, right? And you still have a probability distribution there. But for what we're going to do, we're going to restrict our attention to numeric variables. So x will be a numeric variable whose value depends on chance. The book doesn't say depends on chance. The book says the value is determined by the outcome of a probability experiment. What is a probability experiment? What do the authors call that? Anything where you do some kind of a procedure and the outcome is determined by chance. Right? You roll a die or you select a person from the population, whatever it is. Okay? So random variable, a variable that's random. So x, as a random variable, its value will be determined by chance. All right? So we can list all of the possible values for the random variable x. They are 1, 2, 3, 4, 5, and 6. It's a discrete random variable. Uh-oh, there's that word again, discrete. What does discrete mean in mathematics? Usually it's the counting numbers, but it doesn't have to be. Remember shoe size? We said shoe size was a discrete variable. And what does discrete mean?
Only certain values are allowed.
Good. Only certain values are possible or allowed, right? And there's gaps between those values. What about height? Is height a discrete variable or continuous? It's continuous because any height is possible out to any number of decimal places. But shoe size, no. Number of spots on a die, no. Only 6 values are possible. So the distribution, the probability distribution, gives us all of the values that are possible and then how likely those values are. So we write that as capital P parentheses X. Now remember, when I introduced this capital P, I said P parentheses, and you put inside the parentheses whatever you want the probability of. Well, technically, when I say P of X, I mean Px equal some number, right? But just so that it can be the header of this column, we just say P of X, and then whatever X is, so it's a function of X, okay? Now this is pretty easy. We can fill this in. What is the probability that X is a 1? 1 out of 6, right? 1 out of 6. What's the probability it's a 2? 1/6, and a 3, and a 4, and all the rest are all 1/6. Right? Now there's a couple of properties about discrete probability distributions that have to be met. For it to be a true probability distribution, this has to be true. The probability of X is greater than or equal, actually I want to write that different, is less than or equal to 1 and greater than or equal to 0 for all X. We did this before. We just didn't call it a random variable, we called it an event. So we had probability of an event A is always between 0 and 1. But now we can add a second one. If I add up those 6 probabilities, what do they add up to? They add up to 1, or 100% of the probability. So the sum of all of the PX's, and I'm going to say underneath the little sigma, the sum over all X of the P of X's must be 1. If they don't sum to 1, then it's not a probability distribution. If they sum to something smaller than 1, then you've got a value not accounted for. All right? And because that should be, when you sum across all X, that's the same as saying I'm summing across the sample space. Right? The whole sample space. And when I sum across the whole sample space, I should get all of the possible probability. Okay? So if it meets these two kind of conditions, or these two conditions, it is a probability distribution. Now this is a pretty easy one. Flip a coin. If it comes up tails, let X be 0. If it comes up heads, let X be 1. What's the probability distribution for that? If it comes up tails, X is a 0. So X can be 0. If it comes up heads, X can be 1. Any other values? No. So these two probabilities are 1/2 and 1/2, right? All right. Well, that was too easy. So let's take 3 coins. Luckily, I have 3 coins. I got 3 nickels. Not that it matters that they're all the same, but I got 3 nickels. If I randomize these 3 nickels, and I This is taking longer than it's supposed to. And I count the number of heads that I get out of those 3 coins. Right? Let x equal number of heads. X equal number of heads in 3 tosses of the coin. Now you can, this experiment is exactly the same if I use 3 coins or if I use 1 coin and flip it 3 times. It means, you know, it's the same thing. Right? So number of heads in 3 tosses. What are the possible values of x? I heard too much all at once.
0, 1, 2, and 3.
Good. 0. I could get 0 heads. Right? 1, 2, or 3. P of x. What are those probabilities? What's the distribution of the total probability? That's what we mean by probability distribution. Take a probability of 1 over the whole sample space and distribute it. What's the probability that I get 0 heads?
1/3.
1/3? Good guess, but wrong.
You take 1/3 times 1/3 times
1/3 times 1/3. That's not quite right either.
What's squared?
What? What squared?
The 3 that plays squared.
See, you guys jumped on the 3. What's the probability of heads in a single flip?
2.
What's the probability x equals 0? Write it a different way. That's the same thing as the probability of what happening? All tails, right? So tails on coin 1 and tails on coin 2 and tails on coin 3, right? What do you do when you have an and in a probability statement? Multiply, multiplication rule. So what is this probability of? It's probability, or how do you compute this probability? Probability of the first one times the probability of the second one given the first one. But what about coins? Independent or dependent? They're independent. Whether the first coin landed heads or not doesn't influence whether the other coin's going to land heads or not. So I wouldn't have to put that. Remember, you have 2 versions of, but I like to just be consistent. Probability of tails on the third coin or the third flip given T1 and T2. Tails on the first one, tails on the second one. Right? So what's the probability of tails on the first coin? What? 1/2. Okay. I thought I heard 1/3. I was going to throw my marker at somebody. 1/2. Now, given that we got tails on the first one, what's the probability we get tails on the second one? Still 1/2. They're independent events, so the probability doesn't change. Probability of tails on the third one? 1/2 again. So what's the answer? What? Is that what you said? Okay. I thought you said something else. 1/8, which is 1 over 2 to the third. If you just multiply the bottoms out, you get 2 to the third. Top, you get 1 to the third. Right? So 1/8. Now, using that, tell me the probability that x is a 3. It'd be the same, wouldn't it? Because probability of getting heads is the same as the probability of getting tails. So the probability of all 3 heads is going to be the same as the probability of all 3 tails. But what about these middle 2? I bet if you're clever, you could figure out what they are without really knowing how to work it. First, let me ask you this. The probability of getting 1 head and 2 tails, how will that compare to the probability of getting 2 heads and 1 tail? Same thing, right? So these 2 have to be the same. Because heads, tails is interchangeable in a coin, a fair coin. Right? So how much probability do we have to distribute?
3.
Okay. You're ahead of where I was thinking. I was thinking total we have 1. We've used up 2 8s. We got 6 8s left. If these have to be the same, that 6 8s has to be 3 8s and 3 8s, right? This is actually a random variable that's known as a binomial random variable, which is the next section. So we'll do that on Wednesday. And when we do it on Wednesday, I'll give you more rationale why it's 3 8s and 3 8s. But without that, you even figured out what it was going to be just by symmetry. We know that heads and tails are interchangeable, so they had to match, right? So this is a symmetric distribution. Probability at the tails is the same as the probability in the middle. As the other tail. If we graph that distribution, and that's 1/8, then a 1 is 3 times that tall. There's the graph of the probability distribution. So a discrete random variable, when you graph it, it looks like a histogram or a bar chart, right? And the height of the bar is the probability of getting that value. Okay? That's so easy, right? So easy. What about a problem where you know what, before I do that, let's talk about the mean of x and the standard deviation of x. Random variables, whether they're discrete or continuous, today we're doing discrete, random variables, you can compute the mean of that random variable and the standard deviation of that random variable. Okay, just like for variables that you measure on individuals, like we measured height. We can compute the mean height and we can compute the standard deviation of the height. We can do the same thing with the probability distribution. Now looking at that distribution, the graph of it, it's symmetric, right? Where's the mean in a symmetric distribution? Right in the middle. What's the middle? No, I want a number now. 1.5. So without knowing how to work it yet, we predict that the mean will be 1.5. Right? Now it just so happens if you take these 4 numbers and put them in your calculator and say, hey, what's the mean of those 4 numbers? Guess what you get? 1.5. But if the distribution isn't symmetric, that isn't going to work. Right? But what we need to do to compute the mean is a weighted mean. We did that before. When did we do weighted means? Do you remember? Actually, I don't know. I think it was chapter 2. We did frequency tables, frequency distributions. It's exactly the same idea. This is a frequency distribution. Only instead of flipping the coin 100 times and getting 10 of the 100 and 30 of the 100 and 30 of whatever, we get a probability here, right? Now, looking at this graph, remember the bell-shaped distribution and the standard deviation takes you how far out? Do you remember? Like we did distribution of pulses, and we had this bell-shaped distribution. The mean was here, and we said you go how far out before you get to 1 standard deviation? Halfway down the hill to the inflection point, right? So that's about 1 standard deviation. Do the same thing here. What do you think, just looking at it, what do you think the standard deviation of this random variable x is going to be? It's exactly the same concept. It gives you an idea of how far away from the mean you would expect it to get on average. What's it look like it would be? What did you say? Okay, 2.5. That's not the standard deviation, but that's where it would be. So from 1.5 to 2.5 would be about a standard deviation of 1. And that's what I would agree completely. It looks like standard deviation would be about 1. Right? To there. Now let's compute it. So here's how we're going to compute it. Remember how we did weighted means and standard deviations from frequency tables? You had to do one of these on the test. Hopefully you don't practice the binge and purge method of studying for tests. Right? You cram the night before, and then the next day, you just flush it all out. Right? What do? If you want a weighted mean of the x variable, weighted by its probabilities. Emily, you must have an idea because get your calculators out. What are you doing?
I'm putting the data.
Okay, into what? Okay, so you're putting the x's into L1 and the probabilities into L2. Before, we had frequencies, and we put the frequencies in L2. Same idea. Okay? Now, you can, on your calculator, you don't have, well, I don't know what 1 divided by 8 is, and enter that number. You can actually, in your calculator, just type 1 divide 8, enter, and it'll convert it to a decimal for you and drop it in there. And how many decimal places does it use? 3. So it'd be 0.125. I've done this one enough times to have that memorized. But so you can enter 0.125, or you can just enter 1/8, enter. Right? And then 3 over 8, enter, and so on. And that's what, 0.375? Okay, now how do you get the mean and standard deviation after you do that? Okay, 1 var stats. You're going to do 1 var stats, and then you're not done. L1 comma L2, and don't forget the comma L2, or if this is the old style, the new style is, it just says list, right? List, and you say L1, and then freq list. L2. And then calculate. Okay? So what'd you get for the mean? And the mean, notation is mu sub x, because this is a probability distribution, which is like a theoretical whole population. All right? So we don't use x bar, but your calculator doesn't know the difference. It doesn't know what you're doing, so it's going to call it x bar. Right? So x bar on the calculator, what does it give you? 1.5, which is what we predicted it would be, just by looking at the graph. We predicted the standard deviation would be about 1. That notation is sigma x, because that is think of this as a whole population. If I flip these 3 coins an infinite number of times, that's what the probabilities would be. And so that's the whole population. All right? So in your calculator, remember there's 2 standard deviations in the calculator? It has Sx and it has sigma x. What does it say Sx is? It says nothing. It's blank, right? Well, maybe the calculator did know what you were doing, because you don't want that one. You want sigma x. But why do you think the calculator left that one blank? Look down at the bottom. What does it say n is? 1. N is sample size, right? Well, what it does, when you do a weighted mean in your calculator, it sums up these frequencies to get the sample size. And they sum to 1. So it's you got a sample size of 1. Well, it can't compute Sx for a sample size of 1. Now, this is really testing your memory. Anybody know why? What's that formula for Sx? Oh, God, you said we didn't have to memorize formulas. True, but anybody remember?
On the bottom you have n minus 1.
That's right. Sx, on the bottom, you have n minus 1. And you have the sum x minus x bar squared. So if n is a 1, your calculator tries to compute it, what happens? You can't have 0 on the bottom of a fraction. You can't divide by 0, so it just says, give up. Doesn't do it. Which is okay, because this is the one we want anyway. And what does it say this one is? 0.8660. Okay? So we were predicting, just looking at the graph, that it ought to be around 1. That number is fairly close to 1, so yeah, that looks right. Okay? Okay, so that is a discrete probability distribution. Now let's see. This is page 264. Did I ever turn that on? Nope. So while I'm getting to the page, that'll be warming up. 264. And 264 is, page 264 shows a probability distribution for the sum of 2 dice. If you roll 2 dice. Remember this picture? Right? If you roll 2 dice, and then you take the sum. Snake eyes gives you a 2. A 1 and a 2 gives you a 3. So does a 2 and the 1. All right? So notice that as you diagonal up this thing, all the sums are the same. So what's the probability distribution? I don't want to write it all out, but if I let x equal the sum, what are the possible values? What values of x are possible? Is 1 possible? No, 1's not possible. So 2 is possible. And what's the biggest number possible? 12. And every number in between is possible, right? So I'm going to use some dot dots. 2, 3, dot, 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 11, 12. Right? What's the probability of 2? How many of those combinations are there total? 36, right? 36 combinations. 6 rows, 6 columns. How many of them have a 2 in them? 1. So this is 1 out of 36 possible outcomes. What about a 3? 2. What about a 4? Well, 4 is here. 1, 2, 3, and there aren't any other 4s. A 5 is 1, 2, 3, 4, and so on. Which one's most likely? 7. And what's the probability of a 7? 6 out of 36. Right? So I'll go ahead and put that one in the middle. A 7 is 6 out of 36. And then they start coming back down till you get to 12. And what's the probability of 12? 1 out of 36. Right? This is also a symmetric distribution. Right? But they're not all symmetric. And in fact, a lot of times we're dealing with taking samples from the population and measuring certain things, and you can get any kind of shape to your distribution. It won't necessarily be a nice, smooth distribution. Okay, now, you do for me, I'm going to leave that on the screen, I guess. Do for me the distribution of the difference. Let x, or let's call it y so we don't get confused. Take the difference between the two. And it's always largest minus smallest. So if I have a 4 and a 1, that difference is 3. If I have a 1 and a 4, that difference is still 3. It's not negative 3, right? So you always take largest minus smallest. Write out the probability distribution. I want you to figure it out. Remember, a probability distribution tells you what values are possible and how likely each of those values is to occur.
Can you repeat one more time what you just did? Like the minus thing.
Yeah, let me write it over here. So if I have a 1 and a 4, the difference is 3. Biggest minus smallest. So a 4 and a 1 is also a 3. Got it?
You want us to do it for all of them?
Do it for all of them. I want it like this, a table, where I want all of the possible values and then the probabilities for each of those values. And then I want you to compute the mean and the standard deviation of your probability distribution. So this is what I'm seeing people write down, that 0 is possible, 1 is possible, 2, 3, 4, and 5. No other values are possible, right? And where does a 0 occur? Anytime that you roll doubles, you get a difference of 0. And that happens 6 times. So 6 out of 36, right? Now, what about 1? Where does a 1 occur? It occurs here, here, anytime they're just 1 unit apart. So it's across here and across this diagonal, right? So what's that add up to? There's 10 of those total. Then the 2, 8 of those. That's like a 4 and a 2, or a 3 and a 1, or a 6 and a 4. There's 8 of them. And then 3, 6, and a 4. Only occurred 4 times. And a 5. Just 2 times. What do those add up to? They better add up to 36 36ths so that it adds up to 1, right? If they don't, then you've messed up a count somewhere, because you know by the rules of probability distribution that they have to add to 1. Okay, so then you put this into L1, the x values, and you put the probabilities into L2, then you do your 1var stats, L1, comma, L2. What do you get for the mean of the x's? What? 1.944 repeating. Right? Is this a symmetric distribution? No. So when you graph it, if you graph this thing, you're going to get a bar of 6 by a bar of 10, then a bar of 8, then a bar of 6 again, and a bar of 4, and a bar of 2. Not symmetric. So it makes sense that the mean is going to be over here where the tall bar is somewhere. So getting 1.9, that looks about right. Right? Standard deviation is what? 1.4326. Okay, everybody get that? All right. So next thing I want to look at is there's lots of examples in the book on gambling, but I thought this was interesting. Let's see, I got about 10 minutes left, so let's do this one first. I can't stop on the right spot. Okay, so this is investment plans. So somebody goes in for investment advice, and they say, well, we got 2 plans. We've got plan A and plan B. And then so the guy goes off and does some research, and he finds out that, about 1/10 of the time on plan A, you have earnings of $1,200, but 2/10 of the time your earnings are $950, 4/10 of the time $130, and then once in a while you actually take a loss. Right? Plan B, $1,500. So you have a possibility of making more on this plan than Plan A, because you have a probability of 30% of getting $1,500. Right? But you also have more chances to lose money. Which one would you invest in?
The first one.
How do you know? She said the first one. You might be right, but how do you know? How would you make that decision? I don't want you to go out into the working world and just go, well, I don't know, that looks good. Here's my money. Right? Make informed decisions. The mean of a discrete probability distribution is also called the expected value. So the mean is expected value. And it's a little bit of a misnomer. It doesn't mean that on one play or one investment that you expect to get this number. What it means is in the long run, if you did this over and over again, I would expect the average to be this. Right? So the mean, which we've been computing, I didn't write down a formula for it. We did it with our calculator. But the formula is each value of x times its probability. Right? That's the formula for the expected value. So let's do the expected value and the standard deviation for both of these plans. So do the same thing you did a minute ago. Enter this into L1, this into L2, and get the mean and standard deviation for Plan A. And then do the same thing for Plan B. And you can use L3 and L4 if you want to do all your entry at once and then all your computation at once. And while you're doing that, in terms of investments and stock market and all those kinds of things, the variability in the return is also sometimes referred to as volatility. Have you heard that term? The more volatile the stock, the bigger the risk. So the standard deviation in an investment setting is an idea of what's my risk. Small amounts of variability are pretty safe investments. They don't vary much, but they also don't have the big returns sometimes. Right? So let's see. Have people got Plan A done yet?
Yeah.
All right. So tell me, what is the expected value? 24.5. And what's the units on that? Dollars. So if I invest in Plan A, I can expect in the long run that I'll make $24.50 a year. Okay? What about the variability? What's the standard deviation? 869 and 32 cents. So the variability is huge compared to the mean. Remember, standard deviation is each side of the mean, on average, you'd expect this much variability. So you're fairly likely to take a loss here. If the mean's only 24, the variability is a lot bigger than that. You're more likely to take a loss on Plan A. So let's do Plan B. Anybody got those numbers? Plan B has an expected value of what? 322 even?
Yeah.
Okay. And standard deviation? 863.15. Okay. So Shatali, let me ask you again. Which plan would you invest in?
Plan B.
Plan B. You have a higher expected return with really even slightly less volatility. Right? Now, let's look at this. This is not in the book, but it's one I like to talk about because this is interesting human nature study here. Risk analysis. Are you risk averse or are you a risk taker? And people can be placed into one of those two categories. There's not that much middle ground. It's like you're either a risk taker or you're risk averse, meaning you're not going to take a risk. Suppose you have $1,000 of your hard-earned money that you're going to invest. You've got two strategies. A sure gain of $500 or a 50% chance to double your money, but with a 50% chance to gain nothing. Which would you take? Well, you're not answering because I got to wait till I see the data, right? Well, let's do it. I'm running short on time, so I won't have you enter the data, but you would do the same thing before. The sure gain has expected value of $500. How do I know that? Well, here's gain and probability. This is strategy 2, but the sure gain, you have gain of 500 and probability of 1. It's a sure gain, right? So each value times its probability, you get a gain of 500. Strategy 2 also has $500, right? So the expected value of the two strategies is the same. But this one has a standard deviation of $500. What's the standard deviation up here? 0. Because there's no variability. It's a sure gain. It's always going to happen. There's no variability, right? So which would you take? You take the first one? Then you're risk averse. Anybody say, oh, I'd take that second one? Nobody? Okay, good. So now let's word it differently. Now you've got $2,000 to invest, but now you deal with losses. You can take a sure loss of $500, or you can have a 50% chance at a $1,000 loss and a 50% chance to lose nothing. Which would you take? This is an interesting human nature study that they actually research on, and most people choose the safe strategy when they're talking about gains, getting money back. When it comes to losing, they take the risky one and say, well, I might not lose anything, right? So I'll take that one, since they have the same expected value. These two guys that did it actually won the Nobel Prize for this research. There was a lot more to the research than just that, but it was research in risk and human nature and that kind of thing. But it's all done with statistical analysis of those outcomes. All right, we will see you Wednesday. Don't forget you have homework over 4.3 due tonight.